Problem 3.10. The question is, use equation 3.32 with the definitions of x and p operators to prove equation 3.94 for the n equal to 0 state of the simple harmonic oscillator. Now let me write down these equations for you before we proceed to solve the question. So equation 3.32, I'll grab hold of my pen. So equation 3.32, this gives the variance of an operator. The variance of an operator is the expectation of the square of the operator minus square of the expectation of the operator. So these angular brackets, they denote the expectation value or the mean value. This is equation 3.32, and now let me write down equation 3.94 as well. So equation 3.94 is nothing but the uncertainty principle for the harmonic oscillator. So uncertainty principle, you know, delta x delta p is greater than equal to h cross by 2, and for the n equal to 0 state, it is actually indeed equal to the lowest value, which is h cross over 2. So let us now make use of the wave function that we found that we made use of in the previous question. This was the wave function, and let us evaluate the variances. So first let us work with the x operator. So psi n of x is the following. Where for n equal to 0, this ux function is actually just a constant, which we evaluated in the previous question. This constant right here, this is for the ground state. For the higher order states, the value is different and it is x dependent as well. So this is for the ground state, and let us find out these expectation values for the x operator. So first let us do expectation of the x squared operator. Now x operator is just the value of the position x, so this simply reduces to the following. Now let us plug in these expressions, and let me make use of the substitution that I had used earlier. This substitution, A equals m omega over 2h cross, making this substitution, sorry, this is not 1 over 2, this is 1 over 4. So this comes out So this is the integral that we need to evaluate. Now this is an even function because x squared is an even function and exponential minus a constant times x squared is also an even function. So this entire product is an even function. As a result, we can replace this integral from negative infinity to plus infinity as twice that from 0 to infinity. So this is the following: 2 times integral 0 to infinity of x squared e to the power minus 2ax squared dx. And this, if you recall, is of the form of what is known as the gamma function. The gamma function, which is given as follows. Okay, before that, let me make another substitution. Let me say that let's call some variable I'm thinking. Let's call, I can't use p, I have already used a. Okay, let's just say b. So b is x squared. So this means that db equals to 2x dx. So that means dx equals to db over 2x, which is db over 2 root b. So we'll plug that in. So expectation of x squared is the following. X squared is b, e to the power minus 2a x squared is b, and dx is db over 2 root b. So this 2 cancels out. We get the following. Root b e to the power minus 2ab. Or rather, I should have taken into account this 2a also. Okay, let me do another substitution. I'll say c equals to 2ab So with this substitution, I get the following. Now let us make use of the gamma function. So gamma function is defined as follows. Integral 0 to infinity t to the power z minus 1 e to the power minus t dt. This is the gamma function. So In our case, this is nothing but gamma function of 3/2. Now another property of gamma functions is that gamma of n plus 1 is equal to n gamma n. So in this case, gamma 3/2 is 1 plus half. So this is half gamma half. Now gamma half is nothing but root pi. So this is half root pi. So let us put it all together now. And now I'll plug in the expression for A, m omega over 2h cross. Okay, I think I have made a mistake somewhere or not. No, this looks completely fine. I have put in everything properly. Now let us see what all cancels out. So this 2 to the power 3/2 cancels from this 2 to the power 3/2. And what else? Root pi over here, this root pi cancels out with this pi to the power 1 over pi to the power half from here, and then what we are left with is m omega to the power 1/2 over m omega to the power 3/2 and 1/2. So this gives me, and of course there is one h cross to the power 3/2. There is h cross to the power 3/2 over h cross to the power 1/2. So this gives me h cross over 2m omega. That's the expectation of the x squared operator. Now let us find out the expectation of just the x operator. The position operator gives just the value of the position x, and let us plug in the expression for the wave function that we have. This is our wave function. With this as the value of the constant. Now this, if you see, is actually an odd function. Why? Because this is an odd function and this is an even function. So the product of odd and even functions is an odd function. An integral of odd functions over the entire space from negative infinity to infinity is actually 0. So thus what we have is delta x squared is the following. Since this second term is 0, only the first term survives, which implies uncertainty in x is square root h cross over 2 m omega. Now similarly, we need to find for the momentum operator as well. So for momentum operator also, we need to find out the variance. So first let us look at the first term, which is expectation of the momentum squared operator. Now this is going to be non-trivial because the momentum operator is defined as follows. Minus I h cross d over dx. This is the momentum operator. So this is the momentum squared operator, and this operates on psi. The constant comes out. Okay, minus I h cross squared also comes out. And that's simply minus h cross squared psi star. We are again making use of the same substitution. A equals m omega over 2h cross. Now let's do the derivative. So we'll first take the first derivative. So the first derivative is making use of the chain rule. This is the first derivative. Now the second derivative. Okay, let us take the constant out back again. Minus 2a Now we made use of the product rule. Now we'll again make use of the Gaussian integrals and the gamma functions and the integrals that we performed earlier. So let me write it down. This is the first integral. And this is the second integral. Now here we'll make use of the Gaussian integral. And here we'll make use of the gamma function, the gamma integral. Now let us just recap what these were. Yeah, I had written down the Gaussian integral over here. So the first integral works out to be, this integral works out to be, sorry, I need to change the color of my pen. This integral works out to be root pi over 2a. And this integral we evaluate, the second term we evaluated in the previous part. Let me just go back. Yes, this integral right here we evaluated. This is the exact same integral that we need over here, x squared e to the power minus 2a x squared dx. So let me see where I have written the final result. So this constant term is outside. I don't need that. Okay, apart from this constant term, whatever is remaining, that is the integral result. So this is the integral that we wanted over here. Which is the same as this integral. So this works out to be 1 over 2a to the power 3 by 2, 1 over 2 and root pi. Okay, let us now put everything together. And A is m omega over 2h cross. So this 2 cancels out. Sorry, the h also cancels, at least one h. And here also this 2 cancels. M omega over 2h cross, right? Yeah. So this term cancels entirely with this. And what I'm left with is simply h cross m omega over 2. Now we need to find out the expectation of the momentum operator as well. Okay, minus I h cross I should take out, it's a constant. Now the derivative, making use of the chain rule. Taking the constant out. Now this again will turn out to be 0 because it's an odd function. So this function is odd, this function is even, product of an even and an odd function is odd, and hence the integral turns out to be 0 because integral of an odd function over entire space is 0. So this then gives me the variance of the momentum operator as the following. The second term is simply 0, so only the first term survives. So uncertainty in the momentum operator is square root h cross m omega over 2. Now the uncertainty product delta x delta px is the following. Let me put together the results. Where is delta x? So this is my delta x, and this is my delta px. So putting it all together, now m omega cancels out, giving me simply h cross over 2, which is the desired result. So for the simple harmonic oscillator in the ground state, the uncertainty product is actually equal to h cross over 2, which is the lowest possible value for the uncertainty operator. So typically Heisenberg's uncertainty principle states that delta x delta px will be greater than or equal to h cross by 2, and in this particular special case it is actually indeed equal to the minimum value, the minimum uncertainty product, which is h cross over 2. So in this question we actually worked with the harmonic oscillator and found out the uncertainty relation for the ground state, which happens to be the minimum uncertainty product h cross over 2.